And it's on. So here is Nicolas, here to talk to us about the metaprogramming aspects of the compiler.
Yeah, I'm not sure how much time it will take, not sure how deep it will go, but the idea is to go and have an overview of all the pieces that that make metaprogramming, starting from inlining and into quotes and splices, and how we deal with those in the compiler, and also how the quotes trait is implemented. And yeah, that's the fairly big overview. So we're going to start with inlining. So in the compiler, there are
perhaps make them one big step bigger.
Yeah. Okay.
Yeah.
That's it.
So
okay.
that it's.
Yeah. So in the compiler, there are three parts where inlining happens. So the main place is in the inlining phase, and post-inlining phase does some cleanup afterwards. We'll have a quick look at that afterwards. But we can also inline during the typer phase. So just as an I have the let's wait the pop-up of the Zoom that doesn't allow me to click on the different source.
I think you can
on the side, it will be easier. Yeah.
Ask it to go somewhere else.
Yes. Okay, let's put it here for now. Doesn't bother me anymore. Good. So yeah. So for example, we have this example. It's a simple inline power that just inlines another call to a power function, nothing special, and it gets inline. So this will have two parts. The first is what happens when we type this thing, and how we will first transform a bit this definition. But I'm going to talk about that a bit later. And then there is the part that really takes this call to the inline definition and inlines it. So all that happens mostly in the inlining phase. So the inlining phase is fairly straightforward. It's just a phase that will go bottom up, and we'll find all the inline, the calls to inline functions, basically here, and it will inline them. It will also stop inlining if there are some errors, just to make sure that some errors don't get propagated into code that relies on previous errors. And then everything that really is about inlining the code itself is in this inlines file, which contains this main inline call. And this is really where all the magic happens. I won't go into all the details, but there are some interesting things. First, there are some special cases for some intrinsic macros that just get some special handling. We also have all this binding logic, which I will show in the example. So, for example, when I will get another. So if we have an f that will give us, let's call it n, will be clear, that will give us an int. We don't care about the implementation. Let's say 99, and we. Oh no, actually, I need to. This one needs to be a constant. I will do that with the x. So let's remove this one from here. So here, because we have an x that is possibly side effecting, and we might have other arguments, what we actually do is, let's call it just y to have a different name and not get confused. So this will basically get, before it gets inline, it will get transformed to something like this. Val x equals the y, which will basically evaluate the y and any other argument in the same order. Here and the same for the n. Yeah, and then we actually have the power call, which will get basically this code, and will just replace all the references to those parameters with the ones that we created here. That usually have the same names. If we add inline, let me just use this keyboard. Line like this to the parameter, we're just not going to generate this, and we're just going to inline it directly. But during the transformation in the inlining process, we will first create it, and then at some point we eliminate it and just move it inside directly. There are also some optimizations. So if we know that this is a constant or a direct term ref to something stable, we're just going to inline it regardless of if it's marked as inline. So what do we miss here? So just as a to show how I would just look at what is happening in the compiler. I would basically print typer and inlining to know what was the type, what happened when we typed it, and what got inlined just after a bit later. Let's see how long this takes. What do we do? I know, yeah. Okay.
And it compiles the compiler.
Yeah.
And because you're currently using Zoom, it's going to take forever.
That's actually okay.
Oh,
No, it's actually pretty good with this new one. I give it up to 30 seconds. Let's see. Let's hope. But yeah, Zoom is okay.
Zoom tries to acquire as much CPU as it can.
Yeah.
Oh, okay. It's there.
So here we see this proxy that was generated for the X. So it is prefixed with the name that comes from the name of the parameter, so we can identify them. But then it adds some other string to make sure that there is no ambiguity. Yeah. So I was looking at inlines. Yeah. So we have that. So basically, this lift binding is the thing that lifts that creates those bindings, and then later on we have something that will try to push them down. I won't go into details. And we have a lot of checks for cyclic references in case we try to inline a reference. Let's say if we call the power again here and we never end, then we have a bunch of bit strange tests that test if we stack overflowed and try to recover from that. Plus other kind of checks that also capture the conditions that may come from an inlining that would never end or has reached some maximum limit. As we have this flag that is the maximum limits that we check, that is the maximum depth that we will inline. We also have some special handling for inlining on applies. Okay, this is whenever, okay, another example. So if you have another full. Any and some whatever. So if we have a pattern match that takes this true, then something a bit complex will happen. Yeah, this was an option of something. So so what will actually happen is something that we cannot really write in Scala code, and we will basically generate some anonymous class that contains a def on apply with this signature. So it will look something like let's say like this. This is one of the craziest parts of this talk, probably. And then, yeah, well, yeah, this is actually really, and here we actually call the actual method directly, the foo.unapply directly. So this is transforming a pattern into a term so that we can inline the term. And yeah, and it doesn't really matter what is here, it just creates this that goes down to the pattern matching phase, and the pattern matching phase will just eliminate this anonymous class. And the inlining will just have to inline this call in here, and everything will be inline after pattern matching. Yeah, that's one of the tricky ones. I shouldn't have started with that, but yeah, it was there in the code. Yeah, yeah, okay, that's okay.
Expand a bit the space
Yes.
to the right. More.
So, oh yeah, this is another logic that needs a bit of explanation. So let's say if we have a class or a trait that's true. And then we override it or we implement it with an inline method.
Yes, it would be trait G extend Z or something.
Yeah. So here we have the peculiarity that if we call G direct, the foo on G directly, we can inline it. But if we try to call f.foo, then there is a possibility that we actually need to call this method. So in that case, we will not be able to inline it, and we need this method at runtime. So what we create is a dummy method. I think it was called change, which basically keeps the body and then replaces the foo later on in the pipeline. So basically, we keep the body of this function in there with this special alias of the original function. Oh yeah, I think we don't keep the body directly. We do a call to the inline method so that we can expand any macros if we want to actually generate special code.
Which is actually just gets inlined right,
yeah,
right there and then.
It gets inlined right there and then. Yeah, it's not extremely interesting, but it means that a macro could potentially know that it's in here and know that, oh, I am inlining the version that goes in the default one, and I might do something different, but you should probably not. Also, you might say that a use case would be to just macro detecting that you're in one of those and say, oh no, we don't support that because we really want to be inline all the time. Yeah. But it gives the option to have to override existing methods of any API.
Yeah.
Have some things to drop the inline definitions afterwards, and some things handling positions to make sure that the sources are in the correct. Yeah, so positions are represented with spans, which only contain the indices where the position starts and ends. But we also have to keep track of the source files, which is not kept in the tree, and this takes care of readapting them when we're erasing the trees. Yeah, this is something that needs to disappear at some point when we have full support for the GSR45. This is more a workaround right now. I don't remember what InlineCall trace is. Oh yeah, whenever there is a problem inlining or another inlining, we print kind of the call stack of inline methods, and we can show it in error messages. This thing recovers that or creates that. Then we have a bunch of intrinsic operations that are basically macros implemented by the compiler. I won't go into that. And when inlining, we will use an instance of this class that will basically expand the macro. What do we do? Deal with the parameters. These are also intrinsic macros. Intrinsic macros, and here is where we really start inlining. And here by inline, we get those bindings that I mentioned earlier, these ones, and the expansion. And I'm not sure. No, then it's outside of this method where we get rid of these bindings. Oh, yeah, it's when we call this, we try to get rid of this, but no. Yeah, no, then maybe it's inside of this one. But I don't, okay. I can't follow that one. Is there a question about those specific things that I've covered so far?
The logic that gives more specific types to everything, is it just it's implied by the transformation?
It's implied by the transformation because we are we are transforming this. When we inline, we are inlining the code using a typer or a retyper, and that retyper is taking care of some of those type transformation. Around all those places. And now we go into the inliner, which is really dealing with the creation of those bindings on the inlining the code and modifying anything that needs to be modified while we're inlining the code.
Yeah.
Or refined or adapted in any way. More dealing about the bindings. Probably the biggest part here is the dealing of bindings. And the opaque proxies are something else. Yeah, we have to be especially with opaque types. I won't go into details for that. Everything about inlining, we won't go into those details because it will be too long, but there is some part that I wanted to find. But maybe we can come at that later. Yeah, maybe let's come back later when we go when we look at macros. Then after inlining, we have the post-inlining. We just create some synthetic members for sum of products and singleton mirrors that need to be generated afterwards and were too hard to generate while we were inlining, or impossible. I'm not sure, but we didn't find another solution for this. This thing. So now maybe a bit about we have the distinction between inline and transparent inline. So if you have a transparent inline, then the type of this could be int. If we don't, then the type has to be whatever is stated in the signature. Thank you. And the way we do it is by just inlining the when it's transparent, we just inline the function. We see whatever type that expression has at that moment once it's inlined, and we take that as a type. We probably widen it wherever it needs to be widened outside. But yeah, so this wouldn't be a 7 because it's to be widened to be the function definition, but we could explicitly state that it's a 7. And now when we actually have normal inline functions, what we do is just to add this type here. We basically ascribe it to yeah, you're right. Sorry, to any. So whenever we inline it here, it will ascribe it and it will force the type to be basically this. It's as simple as that. And the other difference is that the transparent are the only inlines that are expanded during typing, the typing phase. In some situations, let's try to put something. So in some situations, if we, let's see. For example, if we have an inline if where we are forced to evaluate this condition, a transparent inline might actually force the inlining of some non-transparent inlining in here. So, for example, if we actually had this, it might force it to be inlined, so that we can actually. Otherwise, it's a compilation error because we don't have a statically known. This, yeah.
This is terrible.
I know. I don't like that one. Yeah. Pushed by everyone that wants to do a partial evaluation using inlining when they should use multi-stage programming to do inlining, so quotes and splices. No, to do a partial evaluation. Yeah. Okay. Let's see where we are. We have the InlineReducer, which takes care of reducing inline matches. Yeah, and other small details. What else do we have? Yeah, so whenever we have an inline match, we'll go there. But yeah, I think it's all about that. Yeah. No. Now let's imagine we have an access to a private field. So if we call this power here, we have to access this field, or we have to inline it somewhere, but we don't have a getter for that field generated in the code by default. So we basically generate automatically a getter. And then what we do is when we're typing this one, we check what members or private definitions we're accessing, and we just change them. And so when they're inlined, they will be pointing to something that can be accessed from outside. And this happens in the PrepareInlineable. Yeah, with these neat accessors, we'll check that if it's one of all those conditions that will need some kind of accessor. I will transform the value of the inline method to make sure that we can use. Do we have some other? And then we have this that basically registers the body of the inline definition as an annotation on the inline definition, which is a way we hook into the tree of the to the AST that is in tasty of the inline definition. Yeah. So we don't really access directly the tree that from the symbol, but we get it through this annotation that helps us load it. This check in a method that checks also if this contains a macro and the macro is correctly formed. And it also checks if we don't have a nested inline method, so an inline method that is defined within an inline method locally.
Oh.
Yeah.
Why is that problematic?
It was technically really challenging.
Ah.
And the usefulness has nobody has really had a useful example where we really need this.
Yeah, I mean, worst case, you can always put it as a sibling in private methods.
Exactly. That's what people do, and that's usually enough. So we have seen, I think, all the things about inlining. Something about inlining? Any question?
I guess you don't. There are some stuff that you reject in inline methods, like returns. Or do you handle returns?
Oh yeah, yes. Yeah, we do not allow I don't think that's in. I don't remember where that's checked, but it's either in the PrepareInlineable or while inline. Not sure, but I remember we disallow it, but I'm not sure where it's checked.
Yeah.
Somewhere. Yeah. Small detail.
In theory, we could implement them using
early.
a labeled
Yeah,
log.
I know, but it's a bit early in the compiler to introduce them. Yeah. I think many people would be happy to have them, but
yeah.
But yeah, we would have to do it and add them to taste. That's if we add them to taste, I think it would be straightforward.
It's almost straightforward, except if the return is itself inside a try.
Oh, okay, yeah,
but then
that can be disallowed.
That can be disallowed.
Yeah, we shouldn't be doing that. Okay. Yeah, so let's go into macros. Understand? Okay. So let's take the example. Yeah, I want to implement it. Oh no, I will have to implement it for an example. Yeah, so I want to do an introduction to two macros on quotes and splices, I will assume that this is known. But I guess quickly read the tutorial before continuing. So I'm going to do this, to split that into two, just for simplicity, to make it work. Yeah, overload it. So something like this. Yeah, let's just assume that this will be a positive number. Yeah, okay. So not sure where to start. From the macro implementation or the, yeah, so let's start from the part that inlines, because we were there. And so whenever we inline this somewhere, let's say here when we had this, now we actually have to inline this. Oops. This code, and this means that whatever is inside the splice needs to be evaluated at compile time, and the result has to be replaced here. So we'll have, so this would actually become x times, they say 2. Yeah, and in this case, I actually needed and here, just to make sure that the 2 gets where it has to be. So yeah, something like that. Yeah. And to evaluate this, we first, yeah, let's see. Inlines. Yes, here we are. Somewhere in the inline, in the inliner, we have this code that will find if we have a splice. Yeah, using some conditions, that splice needs to be at level 0, which means that this splice that is here will not be evaluated because it's at level 1 because it's inside of this code. And we also don't expand macros if there are errors that have been reported by inline. Then we basically take the tree and we expand the macro, and then after expanding the macro, we will retype the expression just to find other inline methods or that might have been inserted by the macro itself, so that we can expand it afterwards. So where is this one? Here. So this.
But when you get there, you've already expanded any macro that were already in the arguments.
Yes. Yeah. You're right. Yeah. This is.
It's still bottom up.
It's bottom up. Yeah. Yeah. It's here basically where we're doing the bottom part. So we do the bottom part. We also try to reduce everything we can. Do some cancellation so we don't do unnecessary work of quotes and splices that are directly nested. And then we check if there is a splice. Yeah, and we only do expand the macro for those conditions. Yeah, and yeah, for safety, we check we're at level 0, and we do some checks about cyclic dependencies that the macro might depend on at runtime. So if the macro is in the same, if this expression is, or more, if this thing If the contents refer to something that is defined in the same file where it's expanded, then we cannot really expand the macro because we need the compile definition for these things. So that's what we're doing, checking here. We're trying to find all the dependencies and checking if we're compiling them right now. And the other part of this logic is that we can support macros that are defined in the same project. So when we detect a dependency to some macro that is in another source file, what we do is suspend the compilation of the current source file, and we continue with the other sources. And once those are complete, we restart the compilation of the ones that have macros that couldn't be expanded yet, and so on until we compile everything, or we get stuck in a loop where nothing can be expanded because everything depends on something else in the queue. And this is what is happening here. Then we have to evaluate the contents of the splice. And for that, we use the splicer, which is another file. We'll look at it just after covering this. So that, we have some simple normalization of some things that when we get inline to generate some ASTs for inline trees. These are used to track what got inlined from which source, and also what got inlined into some code from the current source. There is a logic that will find all the macro dependencies in the context of the splice. Now this is not the complete list of dependencies. These are the static dependencies that we can find from looking at the code that is within the splice. We also have some other dependencies that we can only find at runtime if the macro implementation, for example, here depends transitively on something that is in the same file as the thing that is expanding, for example. So now we can go to the splicer. So the splicer is basically an interpreter for the AST. And it will try to interpret the AST and call the method that is supposed to be in the splice, and has many ways it can fail, and many checks that try to recover what was the source of the failure in case the reflective code fails, in case there was a runtime failure while executing the macro, in case there was a linking error during the expansion of the macro. Usually that indicates that we're compiling something cyclical, where we depend transitively, but on the implementation of the macro depends cyclically on something that is in the current file that we are trying to compile. And so we don't have it, but the compiler thought it was available, because it would have been available if everything would have been compiled and then executed. Yes, so there are plenty of tricky cases in there. And I think we kind of figure out what the source of the problem is fairly reliably. And even whenever there's something missing, we can get information about which class failed and find all the information from the symbol and give a proper debugging error message. So here's mostly error handling. We have to do some things to make sure that the class loader is not changed during macro expansion, and then we have something weird happening. Some things that
there's such a thing as a context. Oh wow.
Yeah, that's something that happened in Scala 2. Someone had some situation where they changed something with the class loader and then it broke macros, and luckily I just had to keep their fix. But it's not
And that's where you have your interpreter.
And this is where we have an interpreter, which basically takes have a position just to know where to report errors in case I have errors, and yeah, the class loader. And then we basically interpret the tree, which is the contents of the splice, which will return as a closure, which we have to then call with an instance of quotes. I'll start by the interpreter. Yeah, I will write it down to so that it makes sense. Yeah, because that's a bit obscure. So the interpreter, which I'm not sure if oh yeah, it's here. So the interpreter basically at the top level just tries to interpret the tree and type tests it with a class tag, which is not 100% reliant, but it's an easy way to find some bugs in the compiler. And to interpret a tree, we already assume that we only have a single call to a static method that receives arguments that are either quoted arguments, literal constants, or an instance of the quotes object that we. So basically, this one. So in theory, we could also say statically something like this, and we would call this one, and we can interpret either expressions, literal constants, or this instance that is provided by the compiler. Okay, so here we interpret a bit the bindings. We have the interpretation of the quote itself, which yeah, we have the two quotes. So there is type quote. So whenever this will not work very well in this example, but if we have a T type, we will pass this instance along, or we might actually have a call to type that off, maybe T or some statically known type, and that's what that interpreter is capable of interpreting. We'll kind of lift that type representation into the compile time. And the rest is basically, yeah, the literal value is just try to convert the value into an actual value. And the rest is called reflectively a method call with many cases in case they're inside of modules, nested in yeah, different ways that they could be defined, and different ways we have to access them and find them through the JVM reflection. Yeah, this it's a few cases of that. Yeah, we inline also, we make sure that we inline all the inline proxies, which are those definitions here that will get inline, but in this particular case, they have not been inlined by the inliner yet. So we just interpret them as if they were inlined. Yeah, and handle basic stuff, basically anything that could potentially be in a method call, but we do not want to implement something complex here. We want to be as lean as possible. Oh yeah, there is also the closure, which is, let's see, in case we define it like this, which also can be from this notation. What is it? Yeah. Expr of no, yeah, Expr of T. Yeah, those are the corner cases that are a bit annoying to support sometimes. Though in many cases because this version actually ends up being compiled as this plus the other version, we can call this one directly. And there are some corner cases where we actually have to call the other version because we cannot access the one we would like to. Yeah, we have to see if that's maybe something we can improve and make sure that we always have the one we want. Yeah, we interpret the args slightly different to make sure that the arguments don't contain function calls themselves, and there are just those quoted arguments, constants, and yeah, and here I think we also have to deal with disclosure, which I think this is most of it. Yeah, the two cases that are special are the interpret quote and interpret type quote, which basically take the AST and put it inside of one of these expression, which is basically the type that implements Expr and the type that implements type. And they keep some other things that I will cover later, or maybe now. Yeah, all JVM reflection and error handling. Oh, so a ton of that. Yes. Oh, yeah. That's
but things we'll have to re-implement if you ever want to compare the compiler using StarJS.
Yeah. Maybe it's as simple as this. I think we can make it have more flexibility, and we can maybe make something easier. Dealing with plenty of different signatures, like arrays. That's this. Oh yeah, all this logic is to try to figure out the JVM signature, so we can load the actual methods. This is dealing with the definition, the class, the linking errors that I mentioned before, where we don't find a class at runtime. And we recover the symbol for it and check if it's defined in the current run to know what kind of error message we should be emitting. I think great questions so far, or too many questions. This is not a file that I have to debug often. At the start, we did a lot of work, and now it's been a couple of years without any major change. So that's just a good sign that we recovered all the bases. Now for the future, if when we will try to add the macro annotations, we will probably refactor this and share the same interpreter, or at least the same core. Just don't care about interpret, splice, and quote for that one, but the rest would be exactly the same. And quotes also. Quotes might be, yes, actually that one might.
I guess the next logical step is to look in these Expr.impl and PrepareInlineable.
So let's go into. So here is this is the library, the user-facing library. So our Expr is basically just this, and we implement it internally, and we handle it internally. And the Expr is basically something that contains the AST and the scope. This scope is basically a stack of identifiers that represents each time we go into a new splice. And this is to find if we created a quote within a splice and then we extruded that that expression outside of the of the quote where it was defined, which means that it might refer to identifiers that are not defined wherever we're going to use it. And this is basically used for that. It is also used for the staging package, which has the run method, which will compile and evaluate a code at runtime. And there we also don't want to have a macro that has some reference to code that we're compiling and then pass it to something that will run it right now, because that makes no sense. And so we also use this as a way to figure out that it's kind of escaped into another compiler in some sense. Yeah, well, kind of literally into another compiler. Yeah. Yeah, I think it doesn't have a type. Is exactly the same. Yeah, the splice scope is.
So you basically cast down to ExprImpl and TypeImpl all the time to.
In the compiler?
Yeah. Or in the implementation of the methods in quotes. I know, because you have
no, there is
I
think there is only one place where we actually need to extract the tree, but yes, we have to cast down. We do have to cast down, but it's I wouldn't say it's all the time. It's in a really specific place in view. Where was that? Oh yes, no, yeah. So no, actually, yeah. So the other part of the is quotes, which contains all the definitions of quotes, which has also two other things inside, which is the quotes on Pickle that we'll have a look later, and the quote matching, which is all the logic to deal with pattern matching with quotes at runtime. Then there are a couple of methods on expressions and on as extension methods. And then the reflection API in there. And this we implement in the compiler with the Expr.scala. And this one is basically a wrapper around a compiler context. We'll use this compiler context for a few things, like ownership and some source position things. And check flags and other stuff. And here we basically, let's see where we use Expr. Yeah, basically this is the place where we use it. Whenever we do a term, we just cast it, and we assume that this expression was provided by an implementation of this QuotesImpl. And we assume that there is no one that will take an implementation of one quoting and pass it into another. I'm not even sure if it would be possible, because the Expr is, actually it might be possible, but the terms are path dependent, so they wouldn't be mixable, but the Exprs are. So we could pass it as from one instance to the other, and that would not be that should not be allowed. But but if you're in the context of a macro, you only have one place where we can get one of those quotes. If you're in the context of a run, then you're getting the same implementation, but someone could try to implement this, but I don't think it's an easy task. It depends on a lot of logic on the compiler, and basically this is just implementing everything that is in the API, and mostly it's just forwarding to the internal logic. It's always a call to something that is already implemented in the compiler. We have also some extra testing things or defaults to make sure that we always have a position. At the end or checks printers for the trees. We also have this unpickle Expr and an unpickle type. Have the pattern matching here. implementation of pattern matching, we will just delegate to tree match, which is imported from from this QuotesMatcher.
Yeah.
Okay. Where to follow next? Yeah, because I haven't introduced quote matching. Yeah, let's see what happens with the quotes while we compile them. So whenever we compile a quote, we have a few phases that will have to do something. So it's mostly staging, splicing, and and PickleQuotes. Staging will check that the levels of the references are okay, that are all references are used in the same level. So yeah, this is at level 1 and then 0 again, so they're at the same level. And if we would have let's eval y equals x, and then we use y,
yeah, that's
and
fine.
y, then it's the same thing. This one would be at level 1, and this one would be at level 1. Oh.
Yeah, but the $y is wrong.
Yeah, it's wrong. Yeah, there. Right. Oh, wait, let me. No, this one is wrong.
This one is wrong.
And this one now is right. Yeah. Right. Yes. Yeah. Okay.
Yeah.
So this is what staging does in a bit hard, but it's the staging phase itself is just going down the tree and finding quotes, and then it delegates to another file, which is this PCPCheckAndHeal, and this one will do all that level logic and track the levels.
Check and heal.
Yes, that's the second part of the
Yeah.
The naming is not the best. I would change it, but now we already have so much that refers to it as heal.
It's for types.
Yeah,
I know it's terms as well.
No, it's not terms. It's types that are term refs getting this one.
Ouch. Yes.
Yes. Yeah. It's
oh my god.
yeah, there is some complexity in that, but let's just keep do an example. Yeah. So what do we need? So we need a T that has a type. So I don't need the expression, but let's just leave it here. And now
somehow you use the T.
Yeah, here, let's say.
In the wrong, but
so this would be the default one. No, but the healing also is not when it's wrong, it's when it's right. So so here we're basically using this T in the next stage. And what we need to do is so this T is of course equivalent to something like this. Using type of T.
Yeah.
Let's name it so it's easier to. And so what we want is to not use this T, because this T in the next stage will not be available, because it's only available from here and it will be erased. So what we are, so what we actually want is to use T and actually T dot underline, which is not supposed to be used by users. This is mostly the internal encoding. And let me just do. So yeah, this is the definition of type, and it has this underlying member, which is just an alias to the type parameter. It's nothing magical. And we basically want to insert this, and this we also handle as if it was a splice, something that will insert the contents of this T in here. So this, if we want, could be read as this in some sense, but we don't, because we never really need to use a splice to insert a type. We only use a type. And we basically can use a type in any subsequent phase stage. So we could actually have a quote and then refer to the inside of that one, which is 2 layers. And so that also has to be handled correctly. So what we do,
in a sense, that's because you know how you can reify a type of T for.
Yeah, basically, whenever we call this, we already have a value that represents the reified value, and at that point, we know the static value of T of the type T.
And so it's trivial to reify it by putting it in a constant.
Yes. So what we actually do to make this process simpler, or in technical terms, is that we say, oh, let's maybe call it T1 is T at underline, and then we refer to all of these with that T.
Yeah.
And so whenever we pickle this, we know that this is an inserted type that will get inserted by whatever expand or evaluates this at runtime. So where was I?
Yeah, so you don't have a term ref to T in the quotes. That would be awkward to.
Which one? Which term?
I mean the
oh,
if you kept T dot underlying everywhere,
yeah,
then you'd have to deal with this path there, which is not really a path anymore once they're inside the codes and stuff like that.
Not only that, the real problem is that if we do that, we also would have to technically create a tree for every type, so that we can have that tree inside. That's more tasty details, because we cannot refer to a type that already exists. We need the tree because we need the specific tree, part of the tree where we are going to insert it, or where there's going to be this hole that needs to be filled with the type. Yeah.
Okay.
So this thing heal type basically is looking at all the types while we're checking the levels, and looking if a type is used in a later phase, and doing this transformation and inserting this. This happens somewhere here in try heal. It's true, not here. If they're implicit, it tries to find implicitly the type of that T, and it will insert it. And if it's used at a lower level, it doesn't matter. If a T is in a different future stage and using a lower level, it's erased, so you don't have to do anything. And it's also not an error. A good example of that is if we have type U, and then we have a splice, and then we call something that actually is using, well, it's using U, right? And then it also has to use type of U, which is the thing that will reify this type. And we'll have to take it from here. Whenever we create this splice, we'll have to pass a reference to this type here. But this is not a use case that I've ever seen in real code. But yeah, the fact that we have to refer in a lower stage to the type of that U as a type of U, what we cannot do is have a term of that U, because there is no that would require some reference to some definition that is in here. And that's why we cannot really create. We can only refer to the type and never create an instance of those types. It's kind of having a type that is more refined than it should, because we always can erase it to something, but then we have a bit more information for the current stage, and the next one we know that it's the type that is at that stage. That's the two things that this healing and check does. We also, the reason why this heal and check is there is that we also use it whenever we're doing this prepare inline and we find that we have a splice. Then we also check the levels in here while we're preparing this to be inline. So we fail at the definition side if this is not correctly staged and not at the expansion side. Um, so next is splicing. Splicing is a fun one. It's a complex one. And before, now it's much simpler to deal with, but before there were those two phases were together and it was a nightmare to debug. So yeah, I think I will go and do a simpler example. I will take one of these examples. Yeah, so this is the example that we care about. So whenever we compile this into bytecode, what we need to do is basically keep this part as an AST, and the rest will not be an AST and will be something that will be evaluated. Right? So we will have an AST that has some holes where things are missing, and we have some code that will tell us how to fill in those holes, what to put inside. But now, that sounds simple, but here, whenever we have references to things that are outside, things get a bit more complicated. So what we do is to transform this.
Transform it to lambdas and store it.
Exactly. Let's call it like y2 type Expr of no, I don't remember. Yeah, double. And yeah, we'll use 2 lines because it's very good. And basically, wherever there is a reference to a quote, we replace that reference to the y by splice y2 to this new one. Now, of course, we optimize those and remove them, but we might actually have we could have something like this in the code where we have a code that contains. So here we would just splice the y2 and not optimize. Yeah, and we have to do something similar with the types like this. We also have to pass them here as types, insert them. Yeah, and the other thing we have to do, well,
the type removed lambda.
We actually do is this. This is the transformation that is happening in splicing. We transform those splices to splices that contain these things. Yeah, this. Let's see if there's some other details here. Yeah, it's basically for the expressions and for the types as well. Yeah, so that's the first part. And then what happens is we create basically a call to this thing. And Pickle, I think it was Expr, that will receive some string that contains the AST and will contain all these definitions, or a lambda that contains all those definitions. Yeah. So what we actually have in that string will be the tasty AST for this. But now we have a missing part, which I will write with these double things, and I will add basically the index of this is what we call a hole, and it's basically the index of the hole if we have several. So we can also have holes that are shared to be the same hole because it basically the hold was a reference to a variable, and so we can share the same thing. And this index corresponds to the index of the lambda that is below here. This could be seen as a list, but we actually compact them all into a lambda that contains all the logic for all the lambdas. And here we actually add additionally. Wait, but we no. Yeah, actually here it be whenever we extract it, it becomes a bit more annoying because we actually have an array of no, I'm not sure if it's an array, but maybe a list of any, and those any are basically these things, and we have to cast them in here, which is ugly, but yeah, but it works. But it's just generated code, so doesn't matter. So here we have y2 equals whatever arg0 to as instance of as Expr of whatever this thing was, double. Yeah, so this is called the fusion. Maybe I can. Yeah, I'll show an example afterwards with this once I clean up the code. But yeah, so we have the index. Then we also have a list here of variables that this hold refers to. In this case, it was only y. So basically, whatever is here, we list them here. This could have several arguments, could be a lambda with several arguments. So this is just a list. And then I think we also keep the type of this expression, which is double. So the type of the spliced expression, because the splice had the information, but the whole we have to add it explicitly because we cannot infer it from the contents if we don't add it explicitly. Because before we could infer it from this. Yes. Well, from this. Yeah, and once we create this AST, well, we actually keep it as a quote that contains holes during the splicing phase. And in PickleQuotes is where we're going to take that quote that contains the holes and just serialize it into tasty format.
Yeah.
So let's where is it? PickleQuotes. Yeah. PickleQuotes will take these things that have holes and we'll convert that to code that looks like this with some lambdas. Yeah, I didn't mention we also have to pass the quotes instance, and here I added several ones and I set the index of the whole, and then yeah, we let this thing to be optimized if there is only one case or other options. Here we also have to semi-erase these types when we're pickling them, because sometimes they refer to types that they are not aware at the time, and those types should be erased. And that's in here, those two things are getting those erased types. Because we add the correct hole with the, and we remove the contents when we are doing that. We extract the, and this is the place also where we, right? Yes, this is also in PickleQuotes. It's also the place where we're creating this call and we're extracting all those things from the holes. And then we put them together, and there is some logic around here that will, yeah, this apply is the thing that will create the call to that unpickling method, and it might optimize it in many ways. For example, if it's an AST that just contains a literal, it will optimize it as a call to a reflect API that will just take the constant. If we have something that is of a primitive type, we will use the toExpr type class to lift it. and similar for those. Yeah, so we pickle we lift them as literal for those two cases, and the rest we lift them using the two Expr type classes. We could potentially do it for more than those primitives, but it's unclear if it's a good idea for users to rely on that being done automatically. Or maybe no, that's not user facing. That might. No, I think we don't have to do anything there. And then there is the one that actually creates Tasty that will go into this other one that is called PickleQuotes, not PickleQuotes. We'll have a look at that, which will create a string basically, or a list of strings. We'll have a look just after this. And then we have to reify this list of strings into source code, so into bytecode or into the AST to create that list that has all the strings from the Tasty, and then generate that call to the unpickle. It's a bit involved, but yeah, that's what's happening. That's what is happening here. We also have some optimization for types, where this one uses a class of or class tag basically to construct the type, because we know that this it's just a static class. No, that's another helper for literals. Yeah. Now in PickleQuotes is where we actually take the tree and convert it into a string. And also unpickle them. We'll have a look at unpickling a bit later, but let's quickly. So the tasty string is basically an array of we take an array of bytes, which is the tasty AST, and we convert it into a list of strings. We have a list of strings because we have this limit in the bytecode size for a string, the length of the string, so we have to split it. Now, I have never found a use case where a real use case where we actually need a string that long. So all the realistic use cases have only one. If we actually reach that length, then we have problems because the AST is too large and the compiler cannot deal with it usually.
Right.
Or it's at that limit where we have to be, where it's really too much.
Anyway, when you eventually compile the methods, that's where that code has been inlined. It's almost certainly going to exceed the bytecode limit anyway.
Unless it's things that get erased for some reason. But we could contain calls to inline methods that then don't generate any code. Only checks. Yes. Yeah. So that's just a detail, and that's why we have a list rather than just a string. And we do the same. We use this decoder. That seemed to be the best option. I don't have real proof that it's the best option, but that's what everyone else is using, at least in their pickling. But I did some tests with other ways to encode the string, and it's always a trade-off for different cases. So I'm not sure if there is a better one. If someone finds something that is better on most cases, then we could replace it at some point. Yeah,
so there's
used that from I found that one from Squid, which took some things from Scala 2. And yeah, I saw that it was better in many cases and used that one. Yeah, awesome. Okay. Let's So now let's go back to the unpickle Expr. So there are two versions because we changed a bit the API to improve a bit to generate less code, and also because I managed to encode it in a slightly different way that is slightly more efficient, reducing some overhead, mainly removing some lambdas that were not needed for all the cases. And then there are some internal things about how we're encoding and unpicking them, on how we expect the tree, the shape of the tree inside of them. And what we do is basically unpickle this, pass it all the lambdas that will fill in the holes that are in that pickled quote, and that will return us an AST, and that's what we're going to put in here with the current scope so that we can track that. And that's the other cast. Wait, oh yeah, this cast is just to have the T because it's already in it. Yeah, I'm similar for all of this. Yeah, I think the biggest optimization was for type, because here we added this lambda, but we actually didn't need it as a lambda, so we simplified it to just. Oh yeah, and we actually optimize it whenever we have we have an AST that fits into a single string. We use a string instead of the list of string, which is the default case on all. Yeah. Now, which one was it? Oh. Yeah, so whenever we no, this is the unpickling. No, there is unpickling here. So here, yeah, we unpickle the tree using the tasty infrastructure that we have. We have to tell it that it's a type. I don't remember why we need to do the distinction. And then we could get that on pickle tree, and we have to do a bunch of things. First, we splice all the types, and then we splice all the terms. It's important to do it in that order, because if not, there were some things that failed type checking in the process of applying this the transformation. Similar for type, but this one only needs to splice types. And yeah, this will just find all the holes in the tree and do either the first version or the second version. I mean, here, yeah, the cast was on the other side on the no, QuotesImpl. And QuotesImpl, yeah, this is where we did the cast, right? No, I cannot see it. Where did I do the cast? Oh no, I don't. Yeah, I don't need the cast because I passed them untyped, and then we do the cast in the implementation of that lambda. Yeah. Yeah, some details about why we changed it and what are the consequences. Yeah, all about replacing types and correctly. I don't remember. Yes, whenever we're going to pass this, the arguments from the, we have arguments that are ASTs, but we need to pass them as expressions. So this thing is just putting them either in a type or in an expression. Yeah, with the correct scope. Yeah, and adding the correct implicit lambda in the lambdas that we need for different versions. Yeah, we have the logic for pickling, which is basically calling the pickler. And we also pick the positions if we have them. And yeah, that's nothing special. When we unpickle, we also use a cache just to make it slightly faster. We showed a lot of improvements when we have recursive macros that get to the same quote many times,
Right.
like in the power one, where we call power nested. So this is handling that and either goes into the unpickle or loads it and then transforms it using the same tree that we had before, and add things to the current context. Okay. We still have the pattern matching. I think that's all about quote picking. So now into quote pattern matching, I guess. And then I think we will be done. Yeah. So let's say we want to check if this this expression has itself a call to some other, to max.power. Some any statically known definition. And we want to extract whatever this value is and its exponents. So this is compiled completely differently than the other quotes, and we have to type check this in a different way. So for type checking in general of quotes and splices, we have quotes and splices. We have this file, which is using a typer, and here it's where we are actually typing quotes. This is mostly creating a desugaring into some methods that we have defined in the library. Defined in the quoted runtime package. So it's those two methods that have the implicit context here. And so the quotes and splices will just desugar the AST of the quote into one of those calls, type check it, and it's done. And it will also update the levels while doing that to track the levels. And that's fairly simple for normal quotes and splices. But for pattern matching, we have to do a lot more. What we do is basically type check the type check the contents of the pattern as an expression, but in a special mode where we know that whenever we find a splice, this will not be a splice, but it will also be a special kind of pattern. So we will be able to know that whatever is inside this splice is actually a normal scala pattern. So that is the first thing that is done in the pattern. And then there is so where to start? Yeah, so I don't want to go into the details, but we basically have to transform this and apply this into some unapply into the Expr match that comes from that we saw here in the implementation of the quotes. We have this, and we basically want to create a call to this unapply whenever we're typing match. So this will actually be type checked and will be transformed into an unapply that receives some type bindings, which will in this case be an empty tuple. And then it's the tuple of the types of each argument here. In this case, it's a double. Or is it a net? No, it's actually the Expr of double because it's the type of the Y that will be available on this side, and then the Expr of int, and here we have Y and E, but actually, technically, we put it inside of a tuple, and we also pass explicitly the using this as a pattern, but here we replace this by a pattern of int or something like that. Yeah, so this is complicated. So here we basically, to create the unapply that will handle this, we have to create a call to the unapply that is defined in here, which has this signature, which basically returns this type of this tuple. So this type that I'm explicitly adding here is the type of these things. This cannot really be written in normal Scala code, but the compiler can generate it, and then pattern matching can deal with it. So this is how we make sure that those types are equivalent, because we don't have any type information at this stage about these two values. And the other part is the pattern itself is kept as a quote. This one is really an expression that is passed to this to the pattern matcher, and we fill this. And wherever we have something that we want to extract, we add a special marker to say, oh, here we're expecting a pattern that we're going to extract, and it's of this type. And this we can pickle it using the usual thing. Yeah, this is not the nicest part to see whenever you're debugging, because it creates a tree that is a bit hard to read.
No kidding.
Yeah, what is worse is that if we use type variables somewhere in the tree or like this, where we want to extract the precise type of this, it will be available on this side. Oh. Yep. Then we actually have T and U defined here in this one. Why do we have two tuples here? Because we want to be able to define all of them before we can maybe reference them here. Yeah, I don't know which one is referenced. Right. Yeah, so this is a bit convoluted, but yeah, once it's encoded, nobody will see it, and it will just get, yeah, this will get erased. So what we end up with is just the logic for decomposing the tuple, and with this the pickled quotes that we're going to pass at runtime to the pattern matcher that will just check whatever scrutiny expression we're comparing with this pattern expression. The shape. Yeah, the shape basically. So it will check, oh, am I calling this method with two arguments? Yes. And then is my argument a double? Is my other argument an int? Yeah, okay, done. That would already not be known by the signature, but yeah, in some cases you need the purchase type. Yeah. Yeah, actually, I think I will have a fairly quick explainer of this part, but yeah, it's a really convoluted part of the logic that does that, unfortunately. And then we have the pattern matcher, which will take evaluate that pattern matching. There are plenty of rules of what is the equivalence. We use this operator to say that a tree is equivalent to another with some conditions. And then we have also a small DSL that says what will be extracted and how to compose them, which is basically reflected from the implementation into the implementation, because we actually use those same symbols here. So it's, yeah, it looks the spec is aligned with the implementation in that sense. Maybe some minor details that are not explicitly the same, but yeah, and those are all the cases that we support and how they match each other. And specifically, yeah, the important things are what things are we going to extract, which is mainly, yeah, the match means that these two things matched and there is nothing else to check, and that there's nothing extracted. The extraction, I think, yeah, it's with the matched with a parameter that says I extracted this from this subterm, and we rely on the order in which this is done to know in which order the elements are extracted. So we always traverse the AST in the same order. We have also some adaptation that we need to do for some other cases, other kinds of calls. So there are those. Give an example. Where was my example? Let's do the simplest one. So here we're saying that we're going to extract a y that might depend on this x. And what this will become is basically the equivalent of
yes.
So yeah, y. So first, y is typed as an expr of int into, let's say, int. So this int is here. This one is actually the type of the body. So we're basically receiving all that, and we can better reduce that to get rid of disclosure. Originally, we had it as this, so that we were forced to better reduce before doing anything, but we changed it to the other, so we could just call show on it and have a nicer debugging experience. It's the only reason. So we do create a bit of overhead while transforming that, but then it's much easier to debug because not you have to create a dummy one to then print it, and yeah, it became a bit. And so yeah, here we support several arguments, and they will all be listed in this list. Yeah. And yeah,
this is beautiful.
And yeah, let's say let's compare what happens with this and with this. So this one ensures that this one will only match if there is no reference to x.
Yeah.
This one will match if there is a reference to x, but not y, exactly.
And also if there's no reference to x.
And this one?
Yeah.
No, this one can refer to x.
It can, but it doesn't have to.
Oh yeah, you're right. It may refer to x.
Yeah.
So it's an expression that may refer to that, and if it refers to anything else that is defined inside of the pattern, then it doesn't match.
Yeah.
And no, that's not the one. This one? No. QuotesMatcher. Yeah. So there is also this environment that keeps track of those of the symbols from one side and the other. That is used also to check that the environment is closed somewhere in the code below. Yeah, and the other thing the environment is used for, is to concrete example. So let's say this is A, this is A, this is X. So whenever we're pattern matching this with this, and we want to make sure that this one is equal to this one, we have to have a kind of an environment that tells us, oh, this A is equivalent to this X in this pattern. and that's what this this environment contains. So this mapping from one to the other. I know I lost it. This end. And it's used in the closed and here. It says that X is equivalent to this Y within this pattern that we're checking. Okay.
So when you implement that down below, you actually use quotes. No, you button match on the trees.
No, the trees. But I use this same notation for So basically, this is
you don't
matching and getting a list of things that have to be extracted, and then it has also to match with this. That is another list that will give me another list of things that need to be matched. And of course, if this one fails, we are not evaluating this ones.
No, for a second, I thought instead of doing case if cond one, that you would do case quotes, and then if cond one, then
I think that's impossible, but it would be really nice.
If you ever have a bug in it, you can never fix it.
No, that's also a reason why we can't really use quotes and splices within the
of course, it's not a good idea
in the code, except for at least within the implementation that is in the compiler. In the library, we can create quotes that will generate something that are not used while compiling the compiler itself. Also, other thing that we don't use macros in the compiler. We do not have bootstrapping issues in case something changes. From one version to the other. And I think we covered all the topics.
Nice.
No, it's really high level. There's one other thing. Let's see. So we have InlineVals, so those are just details. We just check that the right-hand side of InlineVals are actually constants. So, and the InlineVals are not in line with the same mechanism, but they're just in line by the singleton type that they have as a return type. So it's just constant folding. There is something. I don't remember if it's in erasure or if it's still outside. Here we have ProneErasedDefs, which is logic that is mostly for the erased keyword, but it also acts as a way to eliminate every inline method that was fully inline. So basically any inline method that is not retained, or in other words, any inline method that is not implemented some known non-inline interface or overriding. And here we just drop the contents of those definitions, and I think the actual definition is dropped during erasure. So here it's just pruning so that we don't have to look at those trees again. And the contents of the inline definitions. Yep. I think that's all for inlining. Macros.
Well, thank you. That was quite the journey.
Yes, I agree. I don't think it's the simplest one, but at least now there's an idea of if something happens, where it will happen in this pipeline or in which files, because there are quite a lot of moving pieces.
All right, then I guess I will stop the recording now. And where do this here?